So this is my third lecture. And the first half of it really has nothing to do with data assimilation, but it's a very useful statistical technique. And sort of, if you haven't seen it before, it's something you should know about anyway, sort of regardless of data assimilation. That's called the Bootstrap. And then finally, we'll sort of reconnect all these ideas of probability and sampling, and importance sampling, and bootstrapping we've been talking about to discuss the particle filter. And I want to apologize now that the ratio of equations to figures is way too high. But it is what it is. Okay, so suppose we have x1 to xn random variables where they're sampled from some distribution. We can think about those as samples from a distribution. We could also, in this context of bootstrapping, think about them as data. Right? So we'll think about them interchangeably. They come from some distribution f, which I'll refer to as the underlying distribution. And now say that we're interested in some of the parameters of this underlying distribution, right? I mean, that's why we take well, that's certainly why we collect data, right? Is to figure out what's going on, how is that data distributed, and for our purposes, that's really why we're sampling too, is we want to know what's going on with this distribution. Okay, and maybe you're interested in some parameter. It could be the mean, could be the variance, could be the probability that x is bigger than 10, whatever you're interested in. We could calculate from our samples. So we'll call that parameter theta, and that parameter is going to be a rule basically that you apply to your samples, and it's going to depend on what distribution you drew those samples from. So we're thinking about the parameter depends on this distribution. Our estimate of the parameters, like the sample mean or the variance or whatever here, we're going to call g. So that's going to be our estimator, x bar, s squared, etc., of the distribution f is the function g. Right? So it's our estimate for theta is some function g of the samples. And basically, if we have some estimator, like the sample mean or the sample variance, we'd like to know how good it is for the underlying distribution. Right? So this is really sort of a way to test if your subset of data was really good data to choose to find the variance of the underlying distribution, say. All right, so if we're interested in how good an estimator is, we need some criteria to measure how good it is. So we'll look at the mean squared error, where we're taking this expectation with respect to f. We don't know f, all we have are samples from f, so we don't really have a way to take this expectation. Right, and it's a little bit funny, right, we have samples, and we really kind of want to see how good those samples are. So what do we do here? Right, so in fact, this mean squared error is also a parameter of the distribution f. But for a generic theta, this parameter we're interested in finding, we don't know how to estimate it. So what we're going to do is called a bootstrap. Right, and of course, ultimately, if we don't know the distribution, we don't know this parameter that depends on the distribution that we don't know. Right, so we're going to approximate our parameter theta from an empirical distribution. An empirical distribution is going to be a distribution we construct out of the samples we took. All right, we'd really like to know how good our approximation is. So this seems a bit circular. But how do we go about it? So, right, we don't have, in some ways, we're thinking about this as if we don't have more data, we don't have more samples, so we can't sample this underlying distribution. We don't know it, say, right? We only have samples from it. So we're going to sample from an estimate of that distribution, which is basically just our set of samples. All right, so here is what I call an empirical, so I'm going to call that the empirical distribution. Here's what I'm going to call an empirical cumulative density function. Right, and it looks a lot like our definition of a CDF before. So I have the number of samples whose values are less than xi, right? So here's our x values. Here are my numerical values of my sample. So the number of those less than some value x. I'm going to have some minimum, so beneath that I'm going to have 0, right? And then I'm going to have some maximum, which means that if I go to x's beyond that, all of the samples are beneath that x. Right? And this looks like sort of a discrete version of the cumulative densities functions we've seen. And really, to sample this, we use the sort of exact same integrate and invert idea. But what does that mean here? I mean, here it's really even easier. I think about sampling this uniformly, right? So discretely in 1 over n steps, because it took 1 over n steps to climb up this thing. But I pick off one of those, I go over and I see, what value was I at? And that's the sample I use. And it's, I think in practice, probably even easier than this conceptual argument. So our samples form a discrete state space. Maybe our distribution was for a continuous random variable, but now we have a discrete estimate of it. And the associated, so we've talked about probability distribution functions a lot. The version for a discrete problem is a probability mass function. So probability mass function associated with FE. The state space of that is just the samples we have, or the data we have. And because it's an empirical distribution, none of those are favored more than any other. So they all have equal weight, right? And then that might seem a little funny, but this is, if you're a social scientist or something and you're someone who takes data, this is what you don't want to sample from a distribution where someone's answer is more important than someone else's. Right? If you're asking people a question and you want to sample the whole room, you weight them evenly. Right? Overall, when we bin those answers, you're going to see some form of what the underlying distribution looks like. But each individual sample has equal weight. So to go about this process, we let W be a uniform random variable on 0, 1. We multiply that by n and round up. This is a ceiling symbol for round up. That's going to be some integer I. My random variable I'm drawing from an empirical distribution is going to be the ith value on this list of numbers. Right, so this is a kind of a funny thing. Our samples, big X's, right, we've always denoted them with capital X's, they turn into little x's. Right, they turn into the state space. And now I just say, I need index 14. Whatever that value is the sample from this empirical distribution. And the way I like to think about it is you have a bunch of data that you've sampled or collected, and you have all those values and you throw them into a hat. Right? And then you pick one out. And now, okay, this is a sample from your empirical distribution. The key is that you have to throw that back in then. Right? So this is called sampling with replacement. Right? If I don't have replacement and I have 20 pieces of data, then I can only sample 20 times. It's really not telling me anything. Right? So I'm sampling this with replacement. So I have some sample from my hat. I throw it back in. I might pull out that same one again. Right? That's certainly possible, but that's still a sample from this empirical distribution. If our number of samples or data is large, then this empirical distribution should be close to our underlying distribution. And the parameter, and this notation gets tricky. Now we're interested in the parameter of the empirical distribution. Okay, so the parameter, so we're going to look at the same MSE, same mean squared error for the empirical distribution. So here's our rule we applied, and we're going to take samples from our empirical distribution and plug into this rule. This parameter for the empirical distribution, this was our rule for the underlying distribution. If there was a sample mean, it said takes n pieces of data, calculate their mean. Right? So this seems a little funny, but if we go down here, if that's a number, we have our data, we calculate it once it's done. Here we use the same rule, whatever rule we used here, but now these are sampled from the empirical distribution, meaning I could pull that same number out of the hat more than once. And when I do that, I have to see what that does to my estimator. Right? And the problem here, and maybe you can see it, is you have to get the mean squared error, right? So expectations, right? If we're in continuous space, it's an integral. If we're in discrete space, it's a sum. So I have this sum over all the possible combinations. That means I have to think about, okay, I have, say, 20 pieces of data. I pull out the first one, and I pull out the first one every 20 times. That first value goes in here. Right, and then maybe I do it again, and I pull out the first one 19 times, and on the 20th time I pull out a different one. I have to count all of those different cases to get the expectation of this empirical distribution. Maybe it's a little less if there's some symmetry in your function, but basically this is something we're not going to do. Right, so the idea, yeah. Yeah.
Okay, so you just said similar. You're not but on the previous slide, so you said repeat. I didn't quite understand repeat what.
If we want more than one sample. So I draw a new uniform from the empirical distribution.
You have collected, say, 1,000 samples.
Yes.
Capital N is 1,000.
Right.
And now you do this process, which is in that 4 dots.
Right.
How many times?
As many times as you want to do.
Until what happens? This is what I don't know.
Okay, so this is just samples. So now we have to see, so what we want is this expectation that we're not going to do because there's n to the n. So what we're going to do there, so we're going to use our samples from here to do Monte Carlo on this expectation. Okay, so basically what we're doing, we're going to estimate this with Monte Carlo. This is a tricky idea, right? We're estimating our estimate of the estimator, right? I mean, there's a lot of sort of details in the notation that are. The details in the notation are tricky, but the idea really is straightforward and not very hard to implement either. So let's think about the Monte Carlo, right? This number is fixed. I have my 1,000 pieces of data. I calculate a sample mean from those from my underlying distribution. That's some number. That number's fixed. I have my function, which is add up all of the numbers and divide by n, is my sample mean g here. And now those numbers I put in are the ones I draw from my hat, from the empirical distribution. So I'm going to, every time I want to sample this expectation, I'm going to need capital N of those random variables. Those go into my function g. I get one draw of my mean squared error. And now I'm going to repeat that process m times and take the average of y. So this is sort of the generic setup for bootstrapping. Any questions here? I'm going to look at the example next. Well, let's look at the example. If you have questions, you can come back. So again, this doesn't have anything to do with data assimilation, but it's a pretty nice example. So we're going to think about WI being the wait time of the ith customer at the store, say. And we're interested in the long run average. So how long, you have your store open for years and years, how long do your customers wait? So this is our parameter, data that we're interested in. And we're thinking about this going on forever, right? So of course, to estimate that, I have to keep track of how long my customers wait. I'm going to try to use that information. How good is my keeping track of them at saying what my long run average is? Right, that's the question we're trying to ask. So, and here's just sort of reorganizing this above expression. It's really not anything different. I'm just saying D1 is on day 1, what was the total wait time of customers? On day 2, what was the total wait time of customers? And then I need to get this average wait time, I need to keep track of how many customers were on the first day, that's N1. How many customers were on the second day, that's N2. Right, so it's just rewriting it. There's nothing There's nothing more interesting going on, and this should be a little m. So now as little m goes to infinity, I get the expectation of the average number of customers per day, of the average wait time per day over the expectation of the average number of customers per day. Okay, so this is just the setup. This is what we're interested in calculating. All right, so if we have k days of data, so maybe we did this for a month, and you did this for a month, and your boss says, no, that's not good enough, and you need to do this for a year to get something accurate. And you want to say, no, I don't want to do this anymore. I want to show you that doing it for a month is good enough, right? That our error between this estimate of the wait time of customers and the true wait time of customers is small. Okay, so if I have k days of data, I'm going to take the sample mean of the number of customers per day, d bar, and there should be an n bar here, which is this was the average wait, and m bar here is the average customers. Okay, so those are the estimates of the underlying distribution, and they become the parameters of the empirical distribution. So those numbers we calculate and we don't change, right? They are what they are. Right? And we could rewrite it down here, which just brings us back to that first expression. So now for our mean squared error for the underlying distribution, right? This is our estimator, this d bar over n bar, minus whatever the real wait time, average wait time is, right? And that we can't work with, so we go to sampling the empirical distribution. So we have our samples from the empirical distribution, di and ni, and those become our state space. Those become the possible values. So whatever the average wait times per day are for my month, for 30 days, those are going to be the only possible, those numbers, those 30 numbers are going to be the only possible numbers that I'm going to allow this to take on, these little di's. And the same thing for the ni's, the number of customers per day. All right, and then our probabilities for this empirical distribution says any combination, or any day we pick where we get the average number of customers per day and the average wait time per that day, they're all weighted the same. And that's saying that, you know, the first day of the month wasn't somehow more important in our estimator than the last day of the month. Okay, so now we have our sort of our formula for what these averages are. So we have our I'm trying to think, maybe I don't like this line, maybe ignore this for now, but this I like, okay. So we have our average of our states, right? Because our states were from our samples. So this is our parameter for the empirical distribution, and now I'm going to for every day of the month, I have the number of customers and the average wait time per that day on a piece of paper. I'm going to pull those out, k times, and compute this. Right, and then we're going to do Monte Carlo, so we're going to repeat that over and over and over. Right, so the real sort of takeaway message for bootstrapping, I don't remember if I have more. No. The real takeaway message for bootstrapping is we're going to be sampling the data or the samples we already have, right? Which we call an empirical distribution. Another question? Yeah.
The bottom line here is the mean squared error of n.
Mm-hmm.
In underlying unknown distribution.
Mm-hmm.
For di and ni.
As a joint variable that's drawn from the underlying distribution, yeah.
Let's say every is a distribution for d and n.
And I had the same thing repeated twice. One of those should have been for n.
So
Mm-hmm.
The underlying distribution for 60.
Right.
And this FE, the distribution
No. So maybe I shouldn't have said right. So the F here is the underlying distribution forever, every day.
So it's also for distribution for F and N. Sorry, D and N.
Mm-hmm.
Oh, and each of the DIs are supposed to be independent
Right.
identity distribution.
Right. So the number of customers and the average wait time of the customers is IID.
These are 30 IID
Yep.
variables.
Drawn from F.
D is distributed as FE, D and N.
Okay, so if we go here,
Yeah, this D, the capital D and capital N.
so the capital D and capital N, the 30 samples from the underlying distribution become the state space for the empirical distribution. So now our state space has 30 pairs.
So we are trying to approximate these continuous distributions on capital D
Right.
and capital N by the empirical distributions on 30 points.
Yes. Right. And often, and we do it because that's what we have. Right? And really what we want to say is, so if we think about this, if I had, you wouldn't have a problem with this if there were 10 million points, right? Because then I could sample my bucket of 10 million. It would pretty much follow my distribution. What this, maybe you had a bad month and this actually is going to be, too big, this mean squared error. But what this is trying to say is it's really sort of trying to account for outliers, right? Because imagine there was just one outlier day, right? And that very much changed this number, right? Then in your Monte Carlo, well, maybe you got, you're just pulling it out of the bucket, maybe you got that outlier 5 times. And now this number, with that outlier that was much, much bigger, terrible day, huge wait times, that's going to show up a lot, and these numbers are going to look very different. Right? And that's what you're trying to account for, really. Sort of seeing how well, if I shake up the data, sort of I have, how much do things vary? If the number of samples is more, this last line goes to 0. Right, you'd expect the mean squared error to be very small. If the number of samples is big and there isn't some trouble with the data. Right, there isn't a number of outliers, say. Right, so what I'm thinking of is, so we had some distribution that we're sampling. Most of our stuff falls in here. And then say I got 2 way out there. Right, and this is what I took, and then I just averaged these numbers. Yes.
Basically, sum of the total number of DI divided with the sum of total number of NIs.
Yes.
So that would be in a sense considering the entire number of samples, spreading them out, and the whole exam being
Except the way we're sampling this, I could sample, in theory, this probably wouldn't happen, but there's some probability that I could sample this one every time. All k times. Yeah.
But it could be same day counted 20 times.
Right. So this is the key. That now, right? If this is what we have, right? I said in reality. So really these samples are distributed according to this underlying distribution I don't know. What I said is, well, I have these samples. I'm going to pretend that all of these are exactly weighted the same. right? Because I'm thinking this is a typical month where nothing went really wrong. But maybe something went really wrong and there are things far away from your underlying distribution. But I didn't know that when I'm doing my estimate. I just took the average.
But isn't that the whole point of sampling? Like, if replacement is nothing but a population with an infinite population.
It's an infinite population of these 30 hash marks I've written down here.
Sampling with replacement.
With replacement,
That means your population is infinite.
it means you can have, no it doesn't. So you can have an infinite number of samples, but they're all coming from these 30 days. It's discrete and there's only 30 values. I took a month's worth of data and I said this is a typical month. I'd like to estimate this thing I erased because I don't know it. I'm thinking this is a typical month, so I'm going to weight all of these the same. Right, so now with the resampling, I can draw as many of these as I like, but it's going to be the same 30 choices. So the idea is, right, the idea is really to do this. So I take the average of these guys, right, of all the 30, and now I want to take 30 of these, but they might get repeated. So the problem is, what if you repeat these ones that were actually very improbable because you didn't know better, you weighted them the same as the others? Right, so if I did this, my average would be much bigger than the average of the whole population. And that's really what you're testing for, is how good were these samples? That's really what you're testing for, how good were these samples? Okay, that was good. I think we probably needed that. And it's good because I have no more pictures, so I'm happy to draw to try to help out. More questions? Yeah? Yeah. It does not give you F. It doesn't give you F. No. It tells you how, was there something wrong? It tries to prove your point that I don't want to take a year's worth of samples. I just want to take a month. And this is really some sort of measure of outliers. Are there outliers that I shouldn't, that my boss says, no, you actually need to take more data? Well, d bar over n bar is your theta.
Is the theta, and what is this theta?
It's your estimate of theta. This says how, using only the data we have to test against, how good is your estimate of theta? How does it help you what?
This is large number. If theta is 10.5, and this number is 17,000. What conclusion do I draw?
Okay. So this wouldn't be something very useful to calculate a mean in that case, right? You wouldn't, if you have 10.5, if k is 10.5, theta is 10.5. Right, so it's some number.
So that's your estimate of the
Right. Okay.
if I calculate this number, how does it help?
So okay, so what you want is some confidence in that number. So theta is 10.5. I don't know this curve. My average is here 10.5. Right now, if I sample and say most of the time, since there's only 2 out there, I'm only sampling these guys, and I keep getting averages that are 6.8. Right, then there's going to be this big difference, which is sort of telling you your data is not very trustworthy. Your data is not very trustworthy. It's not telling you something about the underlying distribution besides this mean that you already calculated. It's saying, should I trust this calculation of the mean, given that most of the time when I sample my empirical distribution, I get something that's not close to it. That's the question this is trying to address. So is this okay?
Quantitatively, so as I said, you get a number which is like which is d bar over n bar.
Right.
And then you get this number.
Mm-hmm.
And is there some way that you can say that my number 10.5 is not good?
So then it's
0.5 is not goodness.
I mean, so the quantification is the mean squared error. You could use something else. If you had a different metric.
The square root of this, I could write it as 10.5 plus minus square root of this, and that would be a good way to.
Yeah. No, that's not unreasonable. That's not unreasonable. But you could, if you had some other metric for how good is it doing, you could use it. Mean squared error is just sort of the typical one you see. Yeah.
So how many samples will you take?
Okay, so there are some number of samples. We took a month's worth of data. We have 30 samples from the underlying distribution. How much you want to sample the underlying distribution is just up to you. Right, so basically we do Monte Carlo. So I'm going to I need n of them for each of my Monte Carlo estimates of this mean squared error. And then I'm going to do that m times. But that m is up to you in practice. Okay, questions? Yeah.
Does this number help you determine whether you should take one more month of data or not?
That's the goal, right?
So I didn't see how quantitatively you decide that. Right? So you took 1 month's data.
And you told your boss, and he said that mean squared error is too high.
So this is what I didn't quite get. How do I convince him that this is enough?
I mean, this is...
I found a mean squared error which is some number.
Right.
This is 7.
Okay.
How do I say that it's 10.5 plus minus 7?
I mean, I think that's a different... I think that's just an interpretation of what you're okay with. Right? I mean, I think that's sort of a different issue. Right? How much mean squared error are you okay with for your given problem? Which is really the decision maker's issue. To say whether this estimator was good or not. Okay. Moving on. So I'm completely changing gears here. So any variables that had meaning in the first half of the talk, just erase them now. I don't know. How much time do I have? Half an hour. Well, I'll try to go faster, I guess. But this is something, I mean, this is an introduction. This is especially those of you who might be working on a project related to this, we can talk in much greater detail, right? So don't feel like everything you're going to learn about this is going to happen in the next half hour, right? It probably wouldn't anyway, even if I had, a day to talk. Okay, so I guess the sort of purpose of all the talks leading up to now was to give you a foundation in the words that are going to be used in the particle filter. Okay, so our basic ideas are probability distribution, state spaces, sampling, Bayes theorem. We're going to use importance sampling, and we're going to use it in the sense that we're seeking a distribution that looks like the mode or the modes of the ones we're interested in, not this sort of rare event case where we sort of talked about those were two different ideas. All right, so we'll use importance sampling in the sense that we're seeking a distribution that looks like the one of interest. And then we'll use the bootstrap, and the bootstrap is even simpler than the example in the sense that really what I mean here is this idea of sampling an empirical distribution. Right, I have some underlying distribution, I have some samples of it, now I'm going to pretend those are the only samples I have. I'm going to sample that for a bootstrap. One more idea we need is the Markov property, which basically is a statement that the system, the physical system that we're modeling, say, doesn't have memory. Right? If I'm at some physical state, does it matter what happened yesterday, how I got to this state? So there could be scenarios where maybe it would matter, but we're working in the case where it doesn't matter. Right? So in this case, the probability of xj plus 1 given all the states from 0 up to j is just the probability of xj plus 1 given xj. Okay, and I want to sort of keep track because I think the notation might get hairy. So we'll have a cheat sheet over here. So j is our timed index. And we're thinking about j going from 0 up to little n. And that marker is fading, but hopefully you can see that. And our shorthand notation, because I'm not going to want to be writing all of those states from j to 0 every time I need to, is going to be this, let me get another black marker, this 0 colon j. Okay. So let's talk about Markov transitions. And here, in some sense, with sampling, this problem becomes much easier. This can be a very hard problem if I wanted to evolve the full distribution under the model. All right, so we're interested in the probability of the state x as it evolves over time. For independent random variables, so we're assuming our states are independent. We can write them down as the probability of each state. So I can define them recursively like this, given the Markov property from the last page. So for our case, so to sample this guy, right, so this might be pretty complicated, but what we're going to do is we're going to take some samples from this p of x naught. So this is like our background distribution. Right? This is what we're thinking of. And now we're going to push those all forward through the model. Right? So there is some probability distribution here that could be, if it's not linear, we're going to sort of be in a case that's almost impossible to deal with analytically. And when we're not going to deal with it analytically in this talk. But we're going to say if I sample this and move them through the model, then I get to time xj, and it's if I sampled I get to time x1, say, it's if I sampled from this transition matrix, or from this transition probability. If we were in a linear discrete case, this would be a matrix that basically said, would be filled up with, here are the states I'm at, here are the states I'm going to. Do this multiplication, and it will assign the probabilities of transitioning from one state to the next. But going to continuous isn't that much trickier, really. I won't talk about the details, but going to a nonlinear evolution makes this really hard. But for our case, it's easy. We just sample from P. All those samples, we push them forward through the model. Then it's a sample of M. Okay, and then we can combine these above. The same idea above. We have this transition from the j minus 1 to the j state. It's just going to be the product of all those individual transitions. And again, this distribution here is probably very complicated. We're not ever going to write that down as an equation. We're just going to draw samples from it. Okay, so now we have observations. Let's think about how those come in. So our observations are related to the state variable by some observable function. Observation function, just like we've been thinking about all week. So we'll say y is h of x. So now I'm going to say that our y's are distributed according to some distribution function g. Right? And really how we think about this is a random variable y is some observation function of our state variable plus noise. And this G is sort of what noise distribution is that. So if you said your errors were Gaussian, that would be a Gaussian distribution. If you wanted fatter tails, you might do something that looks like a Gaussian with fatter tails. That's called a student T. This could be whatever distribution you like. And we call this function G the likelihood. And really what it's sort of answering this question, how likely was this observation Y given any of the possible states? So really, this likelihood is a comparison between each of the possible states and the data Y. That's how I'll think about it. And again, we can write this down. We can write this down recursively if I think the probability of all of the observations given all of the states is going to be the product of those individual likelihoods. Okay, questions? So these ideas are very similar to what we've seen before. Very similar. Okay, so really our goal for data assimilation is inference. We want to know sort of how good these model states are given the data. Right, so we're going to have this prior distribution that we can't write down probably, but we can certainly sample from it. Right, we draw samples from our initial distribution, which somewhere I called mu. And then we run all of those forward through the model. And we get samples from, for the states x from time 0 up to time small n. Now we call our prior. Our likelihood is just the likelihood of all of the observations from the first up to the nth. And our posterior is just applying Bayes' rule to these distributions. So it's going to be our prior distribution times the likelihood divided by this normalizing factor. Right, and this normalizing factor, remember, was this marginal distribution. Is this marginal distribution over xn. Right, so it's going to be sort of instructive to think about, or just to keep track of what these distributions are functions of. Right, so this is a function of x. This is a function of y. Our bottom is an integral, but it's an integral over x, so really it ends up being a function of y. Okay, questions? Okay, so Monte Carlo. How do we do Monte Carlo for this? So really our goal is to sample all the possible states given all the distribution. And really, sort of what I want, we sort of want the distribution if we can get it. So in some ways this is just sampling to build up a histogram. That might be a larger dimensional histogram, but just sort of to represent our distribution with samples. But we're actually going to need some Monte Carlo in here too. We'll go back to it, but really we're going to need it to do that normalization. Okay, so this is our strategy. We already sort of know it. We take a discrete set of samples from our probability P of x naught, which we called mu, I think, a page or two ago. We move those forward according to the model. That's going to give us the probability of state xj given all the states up to then. And we evaluate our likelihood between samples and observations. Right? So in a perfect world where we had an infinite number of samples, law of large numbers, this would converge. Practically, 2 or 3 observations and this isn't going to work. Okay, so what's going on, and this is sort of a subtle point, and we'll try to think through it today. If you don't get it, I mean, sort of what we do to fix it's more important, understanding that. But let's think about starting this process. Right, so let's think about transitioning from our initial states to the first state. Okay, so we draw our samples from the initial state, we move them forward according to the model. We have our prior, right? We have this term. Now, I can evaluate this function, right? Because really, this is a function of y. So depending on what my data is, my first piece of data, right, I'm going to think about putting all of my prior x1 states in here and comparing them. Right, so that's okay. The problem is if we have a lot of, or if we have samples that aren't too close to the data, which could certainly happen, especially in a nonlinear model, right? And we're going to get samples from this posterior, but I want you to think about this integral on the bottom, and basically what we're doing. So let's think that really what's going in here at the first observation is I have this G is this guy from my first observation, and so I have this G here, and we're doing Monte Carlo on this normalization term. Right, so Monte Carlo says draw from the prior. Okay, we could do that because I can draw from the initial one moving forward in time. Plug into this function and take an average. What if when we plug into the likelihood we get something pretty small? We take an average of that, we get something pretty small, right? And I sort of have this likelihood term on the top too, so I might have some. So this is really. So I might have some small terms on the top that I've sampled, but I have to do this again at the next observation, and again at the next observation, again at the next observation. And what I'm going to end up with is 0 over 0. So I'll have samples from this distribution, but they're really kind of meaningless. So I'm going to end up with 0 over 0. Okay, so the idea is not much different. But the idea is to sort of normalize as you go. Right? And this idea of normalizing as you go, you're actually sampling from a slightly different distribution, which is why it gets this term importance sampling. But what you do is sort of totally logical. Right? It's sort of something we all could have thought of if we were working on this 15 years ago when it was thought of. It's easy to say that in retrospect, right? So the idea is to normalize at every step, and effectively we're going to treat the posterior at one step, so much like we do in the common filter, we're going to treat the posterior at one step as the prior distribution for the next step. So I guess one point I don't think I emphasized, which maybe I should have, was when we were just doing generic Monte Carlo and we ended up in the 0 over 0 case. If I wanted to then, ultimately I get this, the goal, say it worked, and I had this distribution, whatever I was interested in, I'd be integrating against this distribution. My Monte Carlo would weight all of those particles the same, 1 over n. Right? You're at the nothing to reweight them. What we're going to do here, we're going to start with them all 1 over n, right? So we're sampling from this underlying distribution or background. We're going to transition them forward according to our model, so our states move forward in time. And now I'm going to look at each of those states, right? Each of those states at time 1, and say how close was each of those to the model prediction, to the state from the prior distribution. How close was each of those? And that's the likelihood. So really what we're doing here, we're not changing our states at all, right? We had our states initially, we move forward one step, they are what they are. What we're going to change is sort of how likely those states are. So initially we said they're all the same. Now it's like, well, if they were closer to the data, we're going to weight them heavier. We're going to weight them according to the likelihood times whatever the state was, so it was the same in the first step. And then these are weights, so this is a discrete probability distribution, so I need those WKs to sum to what? Probability distribution sum to 1. Right, so I need them to sum to 1, so I'm going to normalize them by whatever this is. Okay, so now instead of going from 0 to 1, we'll go from J to, what I wrote down, from J minus 1 to J, and repeat this process. And this sort of sampling, right, the only thing that's really changed, is that we're updating the weights sequentially, and we're assigning weights to the states, which is sort of equivalent to this idea of a bias distribution we saw last time. It looks an awful lot like what we want to sample, right, because we're comparing to the likelihood. And this is what we do. Okay, so this
bias is given by
effectively. The bias is updated by the likelihood at every iteration. Yep. Or it's given by the likelihood, and that's the product between. So and this is really the difference going forward. So you know, we go to step 1, they're all evenly weighted. Based on the information I gain in step 1, some of them get higher weights. Now I go to step 2. The model moves the states forward. Each state holds on to the weight it had. And that's the prior distribution at step 2. Then I repeat this process of updating the weights. And I get our posterior at step 2. And now I move forward again. They hold on to the weights. I get my states at time 3. I have the prior at time 3. Update with the likelihood. So this is sequential Monte Carlo with importance sampling. Okay, questions? I have a new piece of data, right, the next time. So I'm re-weighting them based on the new piece of data. So they have the old weight from the old pieces of data they encountered, and then they have a new weight from the new piece of data. Okay. So there's problems. Yeah. Problems, yeah.
In the previous case, when you didn't have the weights,
Mm-hmm.
and you were evaluating the whole probability all at once, when these problems that you're just going to describe will occur,
Right.
exactly when you will get 0 or 0.
Right.
Are there
No. But the subtle thing is doing the normalizing every step. So you are going to get problems, and they sort of result from the same place. That, but if I go back to the original problem, I had to, every time I have a new piece of data, I might be multiplying by something very small on the bottom.
Suppose I have 10 pieces of data,
Mm-hmm.
and I just do this.
Yes.
Top and bottom. And I get 0 or 0.
Right.
That will happen exactly when you have the resampling problem. Step of 8 again, or not quite the same.
It's not quite the same. But it's really subtle. So it's not quite the same, but I don't know that I can explain it any better, so I don't want to spend too much time on it, but it is different. But then there's problems, and those problems come from the same place, for sure. So I guess and if you have a large number of samples on a relatively small problem with a deterministic model, this will actually do okay. This will do okay. But it might still actually encounter this problem that basically one of the particles gets all of the weight. Right? One of the particles gets all of the weight. And so think about, if you want to do this integral, say, and so you take 1,000 samples, and only one of your samples is useful at all, right? Then you're not taking 1,000 samples, you're taking one sample, right? If all the other ones have weight 0, then effectively you're taking one sample. So solution is to do bootstrapping, or to sample from the empirical distribution. And this again is, maybe you won't like this, because I sort of emphasized in the first half when we were talking about bootstrapping that we take them all one at a time, right? And they have weight 1 over n, right? Because it's from an empirical distribution. Here I'm doing importance sampling from an empirical distribution. So the weights are going to be these W's, which, let's see, where did we define them, right? So we have these W's, and our distribution is really these states the states of the particles with their corresponding weight. So for resampling, well, we're going to use some strategy to monitor the weights, to see if this seems to be happening. You could do this at every data assimilation step if you wanted. The more you do it, the more error you introduce. But you could do it at every step. But you could basically say, well, If too much of the weight gets on too few of the particles, and you set up whatever those bounds are, then employ this. So to resample is to really bootstrap from this distribution, to draw samples from this posterior distribution, right? And now, though, I guess the difference is now, probably the easiest way to think about it, there's sort of different sort of practical strategies you can use, but probably the easiest way to think about it is I'm going to multiply my capital N samples by the weights, right? And things that are weighted high, there's going to be a large number associated with them. Things that are weighted low, maybe there's 1 or 0 associated with it. So I'm going to get multiple copies of things that are weighted high, and probably 0 or maybe 1 copy of things that are weighted lowly. So we do bootstrapping from this importance distribution, and then we say, okay, now that we've done this bootstrapping, they all have equal weights, and then we move forward. Okay, so I guess let's talk about the bottom note first. If the model is deterministic, then this is kind of a silly thing to do, right? Because I say this is my highest weighted sample. Let's say I multiply n by the weight, and I'm supposed to make 100 copies of this. Then I have 100 copies of the same state. They're going to go to the same place under the deterministic model at the next step. So if the model is deterministic, you're going to have to do a bit of spreading, some sort of sampling around that state. If the model is stochastic, then there's no problem. The noise in the model will automatically spread those out for you and sort of sample in the regions of state space where you want to sample. So this method, so this is referred to as a sequential, so SIR filter, sequential importance resampling filter. It also goes, I think when people say these other words, they actually mean you're doing these 2 steps with it. Right? They don't mean you're doing the original problem, which breaks down almost instantly. Right? So when they say it also goes by the term particle filter and bootstrap filter and sequential Monte Carlo. So all of those really mean the same thing. There are multiple tweaks you could make to these sorts of systems, and I don't have them posted on this talk, but I will post references for you so you can look at different strategies which are often kind of problem dependent. So the one with importance sampling is called SIS, sequential importance sampling. The original one, which never worked, I think is probably what you would call a Monte Carlo filter, but I don't know that there's an actual, no one wants to attach their name to something that doesn't work. And I should sort of go back. I mean, you could, if you did something more sophisticated, a more sophisticated sampling method, you possibly could get samples from that. But you would need to do a lot more work. If you're just doing sort of vanilla, like Amit does. Right, so this is the sort of thing Amit does. If you're just doing vanilla Monte Carlo, it won't work. Okay. I want to add a con. I realized I left off. So pros. And this, there's. I guess I want to say, all the methods, all these data assimilation methods we've been talking about, right? They all kind of have the same flavor, right? And I think ultimately how you make progress as sort of a community on methods is to try to take the best ideas from different methods and do something together with them. Right, so particle filtering has some big cons, but what it does well is there's no linearization. Full nonlinear model, nonlinear observation operator handles it completely naturally. If you're in the stochastic framework, there's no sort of jiggling around of state locations at the analysis step. Your states are where they are. your states are where they are, and that's I guess a nice feature. It's relatively easy to implement, right? I don't need to know those really challenging distributions I'm sampling. I just need some way to sample them. The cons is it doesn't work well in large dimensions. People come up with different strategies to try to push the number where you can say it works up, but that's definitely still a big con. Requires a relatively large number of samples, say as compared to the ensemble Kalman filter. And I guess another con I want to add, that I'll add when I do my fixes, is when you do the resampling, you somehow lose some attachment to the original distribution. So if you're really interested in this problem so if you're interested in sort of the sequential data assimilation, this can do quite well. If you're interested in the problem of assimilating the initial conditions, like 4D-var does, you lose that information when you do resampling. Right, so this isn't going to, you'd have to think about if you really wanted to use resampling if that was your goal. Okay, and before I send this to Amit, I'll put up some references. So specifically there's this guy, Arnaud Doucet, who's done a ton of work in this field. And he has multiple papers and tutorials and books. So I'll put up some references for him. And also, Pierre-Jan van Leeuwen wrote a review paper of particle filter methods for data assimilation. So I'll put up a link to that preprint or something before I give it to Amit. That's it. And I actually have fewer slides than before, but yeah, it didn't.